Hi, we are Group 12 and today we are going to present the Computation Tools Project 1, the sync and simulation of a centrifugal pump. A pump is a fluid machine that transfers mechanical energy into hydraulic energy. For the other hand, the centrifugal pumps are turbo machines used to transport liquids at a specific pressure level. These convert mechanical energy into hydraulic energy, transferring energy to the liquid which facilitates movement to areas of lower pressure. The objective of these projects are designed to simulate a pump that presents a geometrical proposal that responds to specification given for the problem, presents to nomenclature according to English, and determine the operation curve. Our design was based on the manufacturer's BIP. This data was used to design the pump. Our parameters were Bara 1 20.1 degrees, Bara 2 37.18 degrees, 7 blades, D2 0.26 meters, and the figure 3 we can see the blade design, and the figure 4 we can see the blade design. For the simulation we used two different fluids, water and mineral oil, but at the same temperatures of operation but varying their density and viscosity. Here we can have the initial and moderate conditions. We use the density to have to determine the mass flow rate. It's important to say that we use static flow, constant density, and segregated flow for our simulation. Using Inventor and using the dimension and geometry, we created a 3D model of our pump that meet the requirement of the manufacturer, where we then export to file to start CCM to work on the different simulation. Here is the CAD design assembly. Here the CAD design impeller, and here the CAD design the volumes. Now we are gonna see the results and simulations.
The K-epsilon model allows to obtain turbulence length and velocity scales. The transport equations describe the kinetic energy and turbulence dissipation rate. Only one turbulence model was used because the model suggested for mineral oil, despite being more efficient when calculating turbulence in flows with high viscosity, is not very good at modeling systems with high Reynolds and relatively thin meshes, which is our case. Furthermore, it was simulated with both models, and the efficiency and absolute pressure in both simulations were very similar, which means that the mineral oil in our system does not have a very different behavior at the boundary compared to the rest of the pump.
Now we have the results of the simulation software that were obtained from the different flow rates. The first they showed off with a value of 0 cubic meters from an hour. The second is the intermediate point with a value of 70. The third is the manufacturer BIP with a value of 138. The fourth is the free LRE with a value of 170. And the five value is the BIP obtained with for the group, and that have a value with a 152.5. That value is obtained with the result of I said before. The most important values of the graphic is the efficiency and the total head. We can observe that the efficiency, the best value is the free area and the BIP of 12. And in the total head, the higher value is the of the shut off. That is because I have a flow rate of 0, and so have a more high. In the efficiency, we could have a error because the fuel area have the efficiency higher than the other values, and this is incorrect because the most values, the better values need to be the BIP of the manufacturer and the group, the BIP of my group. In the BIP of my group is okay because it's a lower value of Friuli, but is not the the science.
We will now analyze the simulation results with different mineral oil flows. Initially, we observed that the free delivery efficiency is higher. This is due to the fact that there is a proportional relationship between the increases in the mass flow rate and the increase in efficiency. However, it will be expected that the efficiency will be lower in the manufacturer's BEP, or best efficiency point. However, it is assumed that according to the AOR, or the allowable operating range, although the pump can operate and provide a greater efficiency with a higher flow rate, vibrations or premature wear may occur. So to ensure the longevity of the machine, the AOR is reduced, and so this means that it also reduces the manufacturer's BEP. With respect to the total head, we observe that in this case that there is an inversely proportional relationship where as the oil mass flow decreases, the value of the total head increases, giving a maximum value in this case of 240.55 meters in the shutoff. For the Y plus, we observe that in all the cases the values are less than 1, indicating a correct adjustment of the meshing in the pump surfaces, which provides a greater precision in the simulation adjustment. Finally, to compare the BEP proposed by the manufacturer and the BEP of our design, we observe a slightly higher flow values and a lower efficiency, although they are very close, which is to be expected due to the difference in the CAD or the CAD geometry. So comparing our values with the manufacturer ones, we observe a lower head, a lower total head, a lower Y plus, and a lower CPU processing time.
Regarding mesh independence, water flow was simulated in the manufacturer's BEP for three different meshes. A thin mesh with a base size of 0.0056 meters, the regular mesh with a base size of 0.008 meters, and a thick mesh with a base size of 0.0104 meters. Here we can compare the error for the head rise and the computational time as a function of the number of cells. The thin mesh has a higher number of cells, and the thick mesh is the one with a lower number of cells. Additionally, we can observe the error of the efficiency in relation to the number of cells and the computational time. According to both graphs, we are going to work with the regular mesh because the value of the errors obtained with the regular mesh and with the thin mesh are similar, but the computational time with the regular mesh is lower. The thick mesh will not be used because, in spite of a less computational time, the error is larger than the one obtained with the other meshes, and the data obtained with this mesh would be very inaccurate.
Now, in order to realize the cavitation analysis of the manufacturer's BEP with water and mineral oil, we observe that there is no cavitation present. This is due to the fact that observing the graphs and also the range of the total pressure present in both water and mineral oil, we can deduce the fact that the operating pressures of the fluid is lower than the vapor pressures of both fluids, with water and with mineral oil. The same case is present in the shutoff and in the intermediate point. This indicates that there is no implosion of the water particles since the fluid pressure remains below the vapor pressure of the fluid, and for this reason there will be no condensation of the fluid or a phase change.
In the total pressure of water and mineral oil in the free delivery, we can conclude that there is also no cavitation because the pressures obtained are lower than those of the vapor pressure in the case of water and oil. In the BEP of the group has the same case because that don't have a cavitation because the pressures of water, the total pressure of water and mineral oil are lower than the vapor pressure.
The water operating curve allowed us to find the corresponding regression in order to find the BEP flow rate for our simulation. Similarly, the flow rate of our BEP for mineral oil was found with the operating curve. For our conclusions, we have that the regular mesh was used because, although it has a similar efficiency to the thin mesh, which is the closest to that of the manufacturer, the computation time of the latter is longer, which made it more feasible to use the regular mesh. Another conclusion is that only the K-epsilon model was used because the K-omega model does not efficiently model turbulent flows on relatively thin meshes. Also, none of the pumps cavitated because the pressure of the vanes in both fluids is higher than the vapor pressure. Finally, by getting a low Y plus value, it was possible to obtain more information about the data occurring near the pump walls.